coming exams for my part. Okay. Let me see. Before I give you a quick summary, let me just go back to this stress path I put up in my first lecture for illustrating the progression of failure mechanism of liquefaction failure of loose-fill soap. Apart from myself covering this, Professor, you will probably recall that Professor Philip Chung also elaborated on this. I think both parts are important. You might well get a question on this type of stress path with appropriate explanation. As highlighted by Professor Philip Chung, the initial part of water ingress into a loose-fill soap, denoted by the drained face from point A to point B, can be plotted on a stress path of as shown here, in y-axis and x-axis, can be taken to be more or less horizontal, ignoring the slight increase in bulk density when it becomes saturated, followed by the undrained collapse when the collapse surface is reached, associated with the collapse of a metastable structure so quickly that it becomes an undrained process, and hence substantial buildup of pore water pressure, and the only way is to go down towards the critical state strength, point C, in an undrained manner, in a strain softening undrained manner. Hence, the large reduction in available shear strength due to this strain softening, resulting in acceleration with the out of balance force, and hence acceleration of the landside mass with a very low shear strength, hence the destruction and many people killed. Professor Philip Chung highlighted two necessary conditions for this liquefaction failure to occur, namely undrained behavior, and secondly, strain softening behavior. I think I should add also that the undrained condition will only come about in saturated state or near saturated state. Okay, so it has to be wet enough for saturation or close to saturation condition to occur before it can collapse in an undrained manner. And in relation to the collapse or strain softening behavior, it comes about due to a collapsible or metastable structure, which is liable to collapse as represented at this point, liable to collapse at a point which is lower than critical state angle. Okay, and to have that kind of behavior, the material has to be loose enough. Okay, typically looser than the density or in situ dry density corresponding to the critical state dry density. It has to be loose enough, looser than critical state density, in order to have a collapsible structure that is liable to exhibit strain softening behavior in an undrained manner when it is near saturation. So all these conditions are necessary to have a liquefaction failure. Okay? So please bear those key points in mind. So let me now quickly come to a consolidation of the key points I made during the lectures. In my first lecture on lessons learned from Landside investigation, I have explained to you the definition of engineered slopes in the context of Hong Kong. You should know this, or please make sure you know this. Definition of engineered slopes, and as well as the significance of engineered slope failures, what we can learn from engineered slope failures, and what they signify. Okay, again, please look those up. I talked about different slope failure mechanisms, as of course problems and mechanism of rain-induced liquefaction failure of loose fill slope, as explained through a stress bath, as shown here, both by myself and Professor Philip Chung. So definitely worth your while to pay attention to this. I've also talked about in the first lecture the common causes of major failures of engineered slopes as well as minor failures of engineered slopes, together with the improvement measures that should be implemented. In my second lecture on QRA, I introduced to you the difference between individual risk and societal risk, and I've run through with you how to calculate the two different types of risk. For societal risk, you now understand what is potential loss of life and FN curve, I hope. I've also given you examples to illustrate the different applications of global QRA, or sometimes we call that portfolio QRA, as versus site-specific QRA. I've explained to you the risk guidelines for natural terrain landside hazards in Hong Kong. We looked at what it means by the ALAP principle. Strongly recommend you to pay attention to understanding what the ALAP principle comprises. In addition, we talked about cost-benefit calculations in the context of landside QRA. So again, highly recommended that you make sure you understand how to explain how the cost-benefit calculations are to be carried out. And of course, I've run through with you a simple QRA calculations, and I said that you are likely to get a similar, slightly even simpler calculation in the examination. But make sure you understand the simple calculations example that I given you. And you are likely to be tested how to draw the FN curve, as well as how to calculate individual risk. Okay. Apart from drawing the calculated FN curve, you will be expected to also draw the risk criteria for societal risk in Hong Kong. Okay, we've given you some graph paper, so you have to choose the right graph paper to draw out the risk guideline as well as the calculated FN curve for the example. Okay, last week we talked about natural terrain landside risk management. I've explained to you the 6 key landside hazards of natural terrain in Hong Kong, so make sure you know those. We also run through the key characteristics of these hazards, in particular the landside hazards. We talked about the data, the understanding and insights from R&D work, and also lessons learned from landside studies, as well as new tools that we apply in Hong Kong to manage natural terrain landside risk. I explained to you the systematic program for natural terrain Landside Hazards, which is the LANSIP, the LP MIT program, which is unique in the world. We also run through the policy adopted by the Hong Kong government for managing, respectively, the landside risk of new developments as well as the landside risk of existing developments. And most importantly, we run through the different approaches for natural terrain hazard study. In particular, spend a lot of time going through the design event approach, which is the most popular approach by practitioners in Hong Kong. So make sure you understand and be able to explain the design event approach in relation to the workflow, as well as the key stages and essential tasks to be carried out for design event approach. Okay, and today we talked about the current practice as well as the ongoing technical development work for better understanding of the different processes and interaction, as well as providing a basis for further optimization of the design process, which is to come. We talked about the calculation approach for dynamic impact pressure from landside debris and boulders on rigid barrier and flexible barriers respectively. So make sure you understand the calculation. Of course, I've given you a simple example, so look at the example calculation again. Make sure you get the units right when you do the calculation of impact pressure. Make sure you distinguish between the current design approach as compared with the proposed new approach, which are to come but not yet implemented. As I explained, you'll probably be tested on the current approach. Okay. One final advice from me, and that is please try to use your own words to explain the concepts as required by the different questions as far as possible in order to demonstrate your understanding. This will be much better than just simply copying straight from the notes, assuming you find the right page. So it'd be much better if you can try to express in your own way and your own words your understanding. Don't just copy word by word, okay? You get more marks if you can demonstrate good understanding by expressing in your own ways. Okay, so that's all for me.